Hi everybody. In part 2 of this project on the GPS locked frequency standard, we're going to have a look at the build of this project, since I've designed now a printed circuit board for it. And we're also going to have a look at a few issues we had previously. If you recall, we had signal dropout, which was quite bad, and certainly if you're indoors in a workshop, that's the last thing you want if you want a frequency standard. So we're going to have a look at ways we can improve the reception of the little GPS module. I'm also going to have a look at the possibility of converting the 10 megahertz square wave to a sine wave. This was a request I had with some of the comments that were fed back, so we'll have a look at that as well. So the first thing we're going to do is have a look at how we can improve the signal strength. Well, you'll probably recall that when we looked at the little GPS module last time, the modules that we have come with a small passive antenna. These square antennas are called a patch antenna. They're on a ceramic base with a metal backing, and although they're quite good for outdoor use, they're certainly not very good indoors, and as we saw last time, the signal kept dropping out. So what we're going to do is replace this little patch antenna with a active antenna to improve the signal getting to the GPS module. And as luck would have it, the actual socket connection for this patch antenna has available on it the 3 volts that you need for an active antenna. So we're going to utilize that. So we're going to simply unplug this antenna and plug in a replacement, which is going to give us some gain. Now, what I've found is that if you have a look on eBay, you can actually pick up quite cheaply, for around about sort of £4, a active antenna. Here we have one here. It comes with quite a length of cable. This has got about 3 meters of cable, and it's got an SMA connector on the other end. But the antenna itself, this particular device, is an active antenna. It's got a gain of around 28 dBs. It's got a low noise amplifier in there, which is powered by the 3 volt supply. And although this increases the power consumption, you need around about 10 milliamps to drive these active antennas. But what it does mean is that we get a good strong signal to the little GPS module. So let's just have a quick closer look at what we're going to do here. Here we see now both the GPS module with its passive patch antenna there and the active antenna we're going to replace it with. Now, as I mentioned, the connector on the active antenna is a SMA connector with a center pin, whereas the connection onto the GPS module is a small U.FL connector. So we're going to have an adapter to convert it from that to the SMA, and this is the reason for this link here, this little pigtail wire. It's got a U.FL connector on one side, and on the other side it's got an SMA connector. So the first thing we need to do is unplug the patch antenna from the GPS module. Carefully, a pair of pliers, and just pull it upwards. Careful not to bend it, because it's quite delicate. So we remove that, and then we're now going to connect this little pigtail wire here. You can buy these quite cheaply off eBay for around about, I think you get 2 of these for around about £2.50, so it's relatively cheap. So we're now going to carefully plug that into the antenna socket on the satellite module. Make sure you line it up correctly and then press it down. So that's now connected. And the good thing about this is we can now wire this connector now onto the project box, and it gives us access then to fix the active antenna too. But unfortunately, although it looks as though the two will join together, they both have a center pin, so we need to get an inline adapter to convert the center pin to a female. And what I found again on eBay is these little adapters here. They're they convert from screw sort of male to female, but they're in line, so we can just simply connect that onto that one there, and then we find that the connection from the active antenna just screws onto that. So that's the coupling now. Well, I thought I'd just mention that I also found on eBay another active antenna here, very similar to the one that I have installed, but this particular one, it came with the SMA connector there, which is the female type, so that will actually screw straight onto the pigtail lead without the inline adapter. So depends on which one you purchase on eBay whether you need the inline adapter I've used here or not. We'll just have a quick look here at all the components for the project today. I produced two printed circuit boards for this project. The larger one of the two is for the frequency divider network and the 5-volt regulated power supply. Also plugging onto that board will be the GPS module via a little inline connector there, as will the TTL to USB adapter there for programming the GPS module. That'll have a little sideways 5-way inline connector. There's the components there for the 5-volt regulator power supply. The main divider ICs are there, and the Hex-Schmidt trigger IC is there with its holder. These are simply just decoupling capacitors, 100 nanofarads around the board, 100 ohm resistors which we'll use on the outputs, and that's the 0.01 microfarad capacitor feeding the input from the GPS module. Here we have the little button lithium battery there, 3-volt battery with its battery holder, and the blocking diode there. That'll go in that area of the board there. On the display board we've got the liquid crystal display here. I've got the inline pins there that will solder onto the display, and that's the inline socket which will go onto the board itself, so we can plug and unplug the display. There's the 10K contrast preset for the display, some decoupling which I have on the board which is 0.47 microfarad. You'll see here I've got some plastic standoffs and screws. I'll be using several of these on the boards to mount them together. The GPS module, this is the cable to replace the passive antenna here which I showed you earlier, and the adapter. The rotary switch there is a 6-way 2-pole switch which we use to select the frequencies and also to switch the unit on and off together with its knob. And the Arduino Nano there with its inline pins. So there's the components, and I think the next thing I'll do is we'll assemble these components on the boards, and we'll come back and have a look at them. Right, here we now have the display board which is assembled. You can see I've got the Arduino Nano there onto the board. There's the inline connector for the display, the contrast preset there, the decoupling capacitor, and the backlight resistor there. The flying leads coming from this board, just 3 leads. One is for the 5-volt power supply, black is ground, and the yellow lead there is going to go to the TX pin on the GPS module via the main board. The LCD display will now simply just plug into the board. If you wish, you could also insert the connector there, the lead to program the Nano. That could be left in if you wish. There's enough room for that to remain there and for the display to go on, but for the moment I'll just put the display, plug that onto the board. There we go. And we'll just quickly have a look at the reverse side of the board. There you are, not a great deal on there. There's some labelling on that as well. I've also put a little optional pin on that board, as you'll see. That's possibly for a future upgrade at a later date. So there we have the display board ready to plug onto the main module. So let's now build up the main PCB and we'll have a look at that. Here's the main printed circuit board now with all the components mounted. there you can see the lithium battery in its holder there. These are the sockets here. That inline socket there is to plug the GPS module in. I'll show that in a moment. And the one line flat there is for the TTL to USB adapter to go there. There, in that area of the board, we've got the 5-volt regulator power supply and its components. There's the logic ICs for the divider network, and there's the Schmidt trigger IC. The wires coming off will be going to a rotary switch. The blue wire is going to the centre of the rotary switch, and the other coloured wires here, black, red, orange, yellow and green, go to the rotary switch for the different frequencies, starting with 1 megahertz on black and then 100 kilohertz red and going down. There's the green LED at the end of the divider network, which flashes when the frequency output is present. And I've just temporarily soldered on 2 BNC sockets here so we can test the module. The connections that go both to the GPS module for the battery backup and the GPS input there, I've put some single pins in there which will then just plug onto. It makes it easier to take it apart. And same here with the connections to the display board. There's 3 pins there which go to the 3 wires I illustrated onto the display board. They just plug straight in. Now there's some components missing here at the moment because I haven't finalised the output stages for this project, so that's left reasonably blank there, and we'll come back to that at a later stage. I have the standoffs, the plastic standoffs here to support the display board, and some other plastic standoffs as well underneath. I'll just have a look at the reverse side of the board. Right, that's the reverse side of the board. I've printed on the PCB some information that illustrates some of the key areas of the board, which makes it easy when you come to connect things up. Right, so what we'll do now is we'll just quickly show you how the GPS module plugs into the board. Here we have the GPS module, and I've put 2 flying leads on here now, one for the GPS output, the signal frequency, and the red one there is for the goes to the backup battery on the main board. So basically this will then simply plug in there onto the main board in that position, and what we'll then do is we'll plug in the backup battery there, and the GPS input to the main board goes on that pin there, so they just plug straight in. So what we'll do now is we'll position the display board on top of this, and that will just sit on top now. So the display board simply just sits like that, and then all we need to do is plug in these flying leads here to the 3 connectors I illustrated earlier there. So let me just quickly do that. Here we have now the completed assembly. Everything's plugged in, and the display board is mounted on the top there, and I've just bolted with some nuts there either side, just bolting that firmly onto the standoffs which go onto the main PCB below. I'll just tilt it round so you can see the spacing there. There you can see we've got a nice gap between the display module and the main PCB. I found it better to keep that away from the main frequency board to stop any interference. Also, it gives us some room there if we wanted to add another PCB at a later stage for the output stages, and that's something we'll come back later on this project. So that's the modules now assembled together, and we're ready to test. So let's hook it up and test the module. Here we have the module now hooked up to the antenna. What I will do is I'll put the little TTL to the USB converter in so we can program the GPS module. I'll just show you that quickly. That slots into the slot just there between the GPS module. It's just a little tight fit going through those and then just slots in. So basically that then sits there like that, comes out the side, and that can then plug into your PC to program the GPS module, or either directly or via a extension lead. Now what you may find, obviously, when you first assemble all this, the GPS module, if it didn't have the backup battery supply, you will have lost any configuration settings you programmed into it, so you'll probably have to reprogram the configuration in the GPS module to the 10 megahertz output. What I've done for the moment is I've set the frequency of the GPS module to deliver 10 megahertz when it's locked onto satellites, and to deliver 1 megahertz when it isn't locked onto a satellite, just to illustrate a point. And that means that if you didn't want to have the display here, so you just wanted to make the main PCB board without the display board, you'll have some means of knowing when it's locked onto a satellite, and that will be the LED down there, the green LED. It will flicker at 1 hertz a second when you're not locked onto a satellite, and when it locks onto a satellite you'll see it flickering much faster. So we'll just demonstrate that. I'll just connect the power up, connect the battery, and just look at the LED initially. You can see it's flickering there at 1 hertz. Now you see now it's just changed, it's now locked onto satellites and it's flickering quite fast now. So that's the indication that we're locked onto satellites. So as I say, if you didn't want the display board, that's one of the means that you could use. What I've found with the new active antenna now connected, it locks onto satellites much faster, and we seem to get more satellites detected. So we've got 7 satellites here. We're now locked on at 10 megahertz coming out. I now have the module here set up so we can look at the output signals on the oscilloscope here. At the moment I have the oscilloscope connected to the 10 megahertz output, so we can have a look at that. And so I'll just connect the battery supply. Just wait while it locks on. And you can see it locked on. It's now giving us an output on the oscilloscope now of 10 megahertz. We've got the 10 megahertz output. As you can see there, the shape of the square wave is not particularly clean, and it's got some phase error on there as well. And we mentioned that before when we covered that in part 1 of this project. And that's something we can look at a later stage in this project, see if we can clean that up. But the main thing is that the frequency coming out is exactly 10 megahertz, so the frequency is spot on. So as a reference source it's quite good, but the shape of it obviously needs some improvement there. So what we'll do now is we'll have a look at the outputs from the divider network, and I've got the 5 wires here, the coloured wires, and I'll just tap onto each one in turn, and we'll have a look first of all on the black wire there, which is the 1 megahertz output. So let me just move the oscilloscope onto that output. So there we have the output on the 1 megahertz. Frequency is again spot on. We've got a little bit of noise top and bottom of the square wave, but it's a fairly clean square wave other than that. So let's now move down to 100 kilohertz. Right, there's a 100 kilohertz waveform. That looks quite good. Again, the frequency is spot on, and again a little bit of noise top and bottom. So we now go down to look at the 10 kilohertz signal. Right, there we have 10 kilohertz. Again, frequency is accurate, and just a little bit of noise top and bottom, but nevertheless a good square wave. And we move down now to 1 kilohertz, and again the frequency is correct, 1 kilohertz, and the square wave is not too bad. And finally the 100 hertz
output on the green wire, and again not too bad a square wave, and frequency at 100 Hz. So reasonably happy with that. I'd just like to quickly cover off the wiring for the rotary switch. I'm using a 6-way 2-pole rotary switch. The first part of it is used to switch the frequency output, and the second part is used to switch the power on to the unit. That's connect the 9-volt battery. So the first part of the switch, I've left the first position free, so that's the off position, and then I'm switching through from 1 megahertz all the way down to 100 Hz, and that's then fed out as the output frequency to the board. And then the other part of the rotary switch, again the first position is left empty, that's the off position. All the other positions are connected together and connected to the 9-volt battery, which means that that's just acting as a power on switch for the ranges. Now you can get the rotary switches in two forms. One is make before break, and the other is break before make. If you get the make before break switches, it ensures that the power is kept on all the time as you're switching through the ranges. So that's the wiring diagram for the rotary switch. I have the rotary switch now connected to all of the 5 outputs, but for the time being I've left the switch wire going to the rest of the circuitry disconnected, and I'm just going to monitor the center switch of the rotary switch and just look at the signals coming out as we switch through the ranges, just to see what the waveform is like. So we're on 1 megahertz at the moment, and switch down to 100 kilohertz, 10 kilohertz, 1 kilohertz, and 100 Hertz. I'll just switch it back through to 1 megahertz again. There we are. So as you can see there, we've got a little bit more noise now on the top and bottom of this. So obviously the switching is introducing a little bit of noise. So what we'll do now is we'll connect the switch wire to the center of the switch and see what it looks like through the rest of the circuitry on the main board. Right, now the center wire is connected to the switch, and it's now going back onto the main board, and I'm now taking the signal output from the BNC output socket here with the oscilloscope. And again now you can see we've got a little bit more noise top and bottom there. So let me just switch through the ranges. That's 1 megahertz, that's 100 kilohertz, 10 kilohertz, 1 kilohertz, and 100 hertz. So again we have a little bit more noise top and bottom on the signal, and I think what we'll probably have to do is look at some other way of trying to reduce that, maybe put some buffering in as well. So but you can clearly see we've got more noise now top and bottom of the waveform. So we can work on the output stages on this project and try and clean that up. Well, one of the comments I had as feedback was, is it possible to convert this 10 megahertz square wave into a sine wave? And the short answer to that is yes, it is, by using an appropriate filter, because all square waves are made up originally of adding sine waves together. And just to illustrate that point, let me just show you here on the board. I've taken our fundamental frequency of 10 megahertz, and if we now add the higher odd harmonics to that waveform, we will create a square wave. And the way that works is that if we take the first odd harmonic, which will be at 30 megahertz, and add that frequency to the fundamental frequency of 10 megahertz, the effect is the result down here, because as the 30 megahertz is rising here, it pulls that part of the 10 megahertz signal up, and as it's falling down there, it takes the top of the 10 megahertz signal down. So it has this sort of hump result here. And if you then keep adding the next odd harmonic to that, which will be 50 megahertz, it'll take out these humps and square it a little bit more. If you then take the next odd harmonic and keep doing that, eventually you'll get a clean square wave. So really what we need to do is just simply block out all these higher odd harmonic frequencies, and then we're left with the 10 megahertz fundamental frequency, which should be a sine wave. So let's have a look at that process. Right, well here we have our 10 megahertz square wave, and what I'm going to do now on the graph below here is just to plot the fundamental frequency and the odd harmonics. So what we'll find is that at 10 megahertz, the fundamental frequency, you'll have an amplitude there at 10 megahertz. The first odd harmonic at 30 megahertz, you would have another signal there, but not quite as large. And then at 50 megahertz, the next odd harmonic, you would have another frequency spike coming out there, which would be a little bit smaller still. And it's these frequencies that are added to the fundamental frequency that creates the square wave. So if we want to get back to the 10 megahertz sine wave, all we need to do is somehow get rid of these. And the way we do that is we use something called a low pass filter. So if I draw you a graph there, and basically what that's doing, it's saying we allow through the circuit any frequency in this area, but once it gets past here, it blocks those frequencies, it rejects them or attenuates them. So effectively those are removed. Now the simplest of all low pass filters can be made up of a resistor and a capacitor. And that's the arrangement you would have. The signal input goes there and the output's taken from there. Now a resistor would have a fixed value at all frequencies, whereas a capacitor, its effective resistance would change as frequency changes. So the effective resistance of a capacitor is known as the capacitive reactance, and the reactance of that capacitor, or its effective resistance, will get lower as the frequency increases. So effectively this acts like a potential divider and attenuates the output frequency as the frequency gets higher. Now if we have a look here, that graph I've drawn there, which is the frequency band that we want to keep and then reject the rest there, that shape is called the band pass of a low pass filter. And to calculate the values of that low pass filter, the values of the resistor and the capacitor, what they do is they have a point on this passband there where the frequencies then start to drop very rapidly, and this is called the cutoff frequency. I'll call it FC, and the cutoff frequency is calculated when that point there is at 0.707 of the maximum. Other people may refer to that as 3 dB. So as the signal drops by 3 dB, it hits the cutoff frequency, and thereafter the frequency falls off rapidly and attenuates the higher frequencies. The formula then to calculate that cutoff frequency is FC is equal to 1 over 2 pi RC. The resistance in ohms and the capacitance in farads, and with that formula you can calculate the cutoff frequency there. And if you were to transpose that formula around, you could calculate the value of the capacitor or the resistor. So if you choose a particular resistor, say you choose a 1 kilo ohm resistor, you can put that in the equation here. You know the frequency. If you want the cutoff frequency to be, say, at 15 megahertz, then you can put that frequency in there. You can transpose the formula, so the C would come there and the FC would go below, and you could calculate the value of the capacitor in farads. So the The capacitor is in farads and the resistance is in ohms. Now that is the simplest of all low pass filters. If you wanted to improve that low pass filter, what you could do is you could replace that resistor with an inductor. And the reason behind that is, unlike a resistor, an inductance has reactance. Its effective resistance changes with frequency. So the inductance there, as the frequency increases, the value of the effective resistance of that inductor also increases. So we have a situation here now that as the frequency on the input here starts to rise, so it gets to higher than 15 or 20 megahertz, the effective resistance of the inductor also increases and the effective resistance of the capacitor reduces. So not only have we got a potential divider there network attenuating that signal, it attenuates it more as the frequency increases now because we've replaced the resistor with an inductor. And what we're going to do today is use this type of a circuit to try and attenuate the odd harmonics from our 10 megahertz square wave. The other thing we can also do with this circuit is we could add another capacitor here. And that will improve the rejection of the higher frequencies. Again, those will be taken to ground through that capacitor. As the frequency increases, the reactance of that capacitor also reduces. So this is the type of circuit that we're going to use today to try and reject the odd harmonics from our 10 megahertz square wave. The values I'm going to use in this particular case, I'm going to use a 1.5 microhenry inductor, and the two capacitors will be exactly the same value of 220 pF. Now these type of low pass filters are passive low pass filters. They have no gain in themselves, in fact they have losses. So whatever signal you put in on the input, even at the passband frequencies here, you will still get some loss of signal on the output. And the other thing that affects these type of filters is the input impedance and the output impedance of this particular circuit. So we really need to make sure that the input impedance and the output impedance are particularly high on the input, so you don't affect the circuitry before that. So although we're going to use this type of circuit today just to demonstrate how this works, when we finalize the project we will have to modify this to effectively put some buffering there to stop it affecting the rest of our divider network and the frequencies on the other frequencies of 1 megahertz and 100 kilohertz and so on. So let's have a look now on the oscilloscope at the 10 megahertz signal and look at the harmonics, and then look at the effect of adding a simple low pass filter like this. Here we now have the oscilloscope connected to the 10 megahertz output. As we mentioned earlier, the waveform isn't particularly clean, but it is exactly 10 megahertz, and there's a little bit of phase distortion there as well. And below I'm now looking at the FFT trace, which is showing in frequency domain there, and you can see the highest spike there in the center. That is the 10 megahertz frequency spike, and as we come down you can see the harmonics spikes coming down there, and you can particularly see there a larger spike there, which is sort of third harmonic, another larger spike there sort of around about the fifth harmonic, another spike there which is around about the seventh harmonic. So they're the odd harmonics, and you've got some other harmonic distortion coming through as well, probably due to the phase error on that input waveform. You'll notice that on the below 10 megahertz we've got very little coming through there, so virtually all of the additional frequencies are coming through above 10 megahertz. So what we're going to do now is I'm going to connect a low pass filter in between the output from the 10 megahertz signal and the oscilloscope, and just see if we can attenuate those odd harmonic frequencies they're coming out. And just look also what happens to the shape of the 10 megahertz waveform there. So the filter I've made up here on this breadboard is made up of two 220 picofarad capacitors and one 1.5 microhenry choke. So you've got the capacitors going down to ground from either end of the 1.5 Henry choke. So we're going to put the input frequency on that side, and we're going to check what's coming out on the other side of the inductor there. So let me first of all connect the 10 megahertz input to the input of the low pass filter, and now I'm going to connect the oscilloscope to the output. I think you can see here straight away that the shape of the waveform is starting to resemble more of a sine wave, even though we've got some phase distortion there. And also, when you now look at the FFT trace there on the oscilloscope, we have had some attenuation of those harmonic frequencies. Now we could actually improve on this by adding more filtering here. I'll just give you a little demonstration. If I add another 220 pf capacitor from the output, and then move the oscilloscope to that, you can see we've got a little bit more attenuation there of the output, and there's the fundamental frequency of 10 megahertz. Now this is not ideal at the moment because we've got all these floating wires coming from the board, so we're picking up obviously interference as well. So this arrangement really needs to be on the main PCB board to overcome any sort of noise that we're generating on these leads going to the board. But I think what we'll do is we'll have a look at the types of low pass filters we can use for this project. This particular one is a passive low pass filter, so it's got no gain to it. In fact, it'll reduce the gain of the signal, and there's no buffering to it either, so it will affect the other frequencies coming out of this module. You know, our 1 megahertz, etc., will also be affected by adding this filter on the output. So what we're going to have to do is probably give some buffering to that to stop any interference to the main board, and also maybe give some gain as well to the filter so we don't have any reduction on the output. So that we can have a look at of the improving the filter arrangements in the next part of this project.
Right, well, I'm going to leave part 2 of this project there for today. In part 3 of this little project, we'll go in a little bit more detail with the filtering, the low pass filtering for the 10 megahertz sine wave, and we'll look at different types of filter, active filtering rather than passive filtering, and I'll also cover off the information you'd need how to calculate the values of the components for that in a little bit more detail. We'll also look at trying to clean off the square wave from the switched output to get rid of some of that noise, maybe by adding some buffering there, and any other changes we decide to make to the circuit. But for now, I'm going to leave it there. I'll put some links down below where you can download both the schematic for the project so far and also the layouts for both of the printed circuit boards if you want to have a go at building one of these yourself. But for now, I'm going to say cheerio. So if you found this of interest, please give me a thumbs up and subscribe, and I'll see you all again soon next time. Bye for now.